Okay, fine. Just to say, I've been advised to keep my video off so that we avoid, clogging the bandwidth and not being able to maybe have a good session. I think last time we had some issues with the internet right at the beginning. So to avoid that issue, I will not put my video on. So let's delve in. So first, just a quick recap of what we did yesterday. I don't know if everyone who is on the call today was also present yesterday. But if you haven't, we'll just do a quick recap. So first, let me just say that the resources will be posted in this drive. I've shared it again on the chat, in the chat window. And this is where you will find the PowerPoint and the resources we use in the class. Let me just share my screen. Give me 1 second. Okay, so when you go to the link that I just shared, you will see that there is a PowerPoint. Now, this PowerPoint will be updated. So, for example, I've updated it for today with the material that we are going to go through today, but it's the same PowerPoint. So hopefully by the end of this module, you'll have all the notes that we have been through. And then in the folder, just quickly, let me see what's on the, I meant Friday, that's right, apologies. Yeah, when we met on Friday. You also see a folder. Now, last time you did not have this folder before the session. So what that meant is that during the session, you had to catch up with the code and also with the PowerPoint. So there was quite a lot. So hopefully you've managed to download this folder now. So this folder has 2 examples. The first one is an example about decision trees. And you have some R files in this folder. So you have the R file, which is the code. You have the project, and the data comes from an R package. So that was the DAG package. So we're going to look at this again today, just to try to get the feel from the audience, whether they've managed to download these files and whether you've managed to run them. So the only thing I've added for today is this Excel spreadsheet. And I can explain why I added that Excel spreadsheet in there. So this was the first example. This was about creating a decision tree for predicting whether an email is spam or not. And we were using a simple data set for that. The other example, again, was very intuitive, and we didn't look at it in class. So maybe we can revisit this today. So this was about predicting weights from height and gender or sex. And again, you have the R file in the folder, and you have a file with the data. Now, there are other data sets that are available, but it would be good to run this with the data set that I've given you. I know yesterday, on Friday, there were some questions about where is the data set and so on. So let me now go back to the PowerPoint to see what we covered. So basically, these are the 2 examples we used last time to look at decision trees and regression trees. So let me ask the audience whether they've managed to download this information and this data, and whether they've managed to run some of this code. If you could, indicate in the chat or put a hand up. a minute, okay. So some people said they've managed and some people not, maybe. Okay. Okay, let me go back to what I shared with you. Share it again. Could you try with this folder? They should all be there. Yeah, they should all be there. And you should be able to see the PowerPoint and the two folders. Let me just also check. Okay, great. Okay, good. All right, so let's go back to the PowerPoint and see where we are. So I'm going to go to the content slide. Okay. Okay. I hope you can see my PowerPoint. Can you see my PowerPoint?
Yes.
Yes, we can.
All right. So actually, last time we went through quite a lot of material in a short time. So we didn't have time to do questions. So one thing I think we should do better today is we can take some of the questions that you had. I don't know if Joel or somebody from APHRC had time to write down the questions that were in the chat last time. And if we do have a list of them, we could discuss them. If not, you can just ask again when we have the question time. And then there's also a request that we have a break. So that means that just to split the session. Last time the intention was to do 2 hours, but actually we went over that. We did a bit longer. So let's try to have a break in an hour from now so that people can also have a healthy break, right? So we covered what is supervised machine learning, and we talked about the decision and regression trees. And today, what I wanted us to look at was to cover the random forests that I think one of the people in the audience mentioned that. Because that's linked to decision trees, and after that to go on to cover support vector machines. So that's the plan for today. So what I want us to do is to go back to those trees because those are important. But okay, before we do that, let's go back to the concept of supervised machine learning. So supervised machine learning is about, let's go to this one, right? Is about taking in a lot of training data. And this training data has the shape of data points and label. Passing on this data through an algorithm that builds a mathematical representation of this data. So either, for example, builds a line of regression, or it builds a decision tree, or it builds a super vector machine. So it builds a mathematical model that it is able to find the best fit for your data. And the next time when you see a new data point which has not been labeled, the algorithm is able to correctly label that piece of data if it's classification. If it's prediction, then it will be able to give you a prediction with respect to the task that you have. So this is what we discussed last time. We also talked about this concept of error. So this concept of error applies to classification problems. And there are 4 types of outcomes that a classification can have with respect to your data points. So we talked about these true positives as being basically all the ones that the model was accurate to classify them as they should have been classified. And then we have the true negatives. So these are the ones that were classified again as not being, this is for binary classification, as not being spam, for example. So emails that were not spam and they were classified as not spam. So those would be our true negatives. And then we have these false positives and false negatives. And we talked about them last time and how we can measure the accuracy of a model with respect to these 4 types of outcomes for data points. So we talked about the Cohen's kappa index and so on, and other measures. All right, the other thing that we also said in here is that one of the common ways of building a machine learning algorithm. So we have lines of regression. So that's something you're familiar with from statistics. So we can create a linear regression model that best fits our data. But when the data has multiple features, for example, then we would need something more. So we talked about these decision trees and how we could build them. So first we tried to look at what they mean, so how we could read one. And what they were doing, they were classifying data. So here, for example, there was the data set from the Titanic, classifying whether a specific person on the ship had, the likelihood of that person to have died or survived. And you can see that in the inner nodes, we have these features or characteristics that allows us to split the data set incrementally in smaller and smaller parts until we manage to get to the result that we are looking for. The other thing I was showing you last time is this CART algorithm. So the CART algorithm is implemented by many machine learning libraries. And we looked at this algorithm slightly together, not for a long time, but we talked about the Gini impurity index and how this algorithm would be able to use that to build a tree. So what I thought I should do is to show you something before we move on. 1 minute, let's have a look. Let me stop sharing. So I want to show you the Excel spreadsheet that I added into your folder, the decision folder. Okay, so I hope you can see this. Or maybe what I could do is let me share my whole screen so then we can switch from one part to the other. Just give me 1 second. Right, so remember that what we said about this algorithm, that what this algorithm does is taking your data set. So in this case, it will be your training data set. So taking your training data set and is building a decision tree on top of that. But your data set has many features. So potentially, you can split your data set in smaller subsets, right, in many different ways. So there's more than one tree that you could build. And also, you saw in the R example that we gave, not all the features were used when creating that decision tree. So one, we need to be able to find a way to know how to split this tree. So you can see here that this tree starts with the root node. So the root node contains all the training data and recursively splits that training set into smaller subsets. So if you can imagine, each level of the tree is one split. And we said last time that this tree is binary, right? So now what we need to decide, right, is like here, if we need to decide what should be the criteria for the first split, for example. So in this case, the criteria was on sex. Is the person male or female? And we have to then have a measure to estimate how good this split is, right? And we keep doing that. We keep doing that until we reach a stop criteria. Okay, let me just have a look. Maybe somebody can give the resource link to people who join later in the chat, because it'll be difficult for me to keep doing that during the talk. All right, so that's what's happening. Yeah. Now let me show you how this could be simulated with Excel. So it's not necessarily complicated. So what I've done is I downloaded the training data set. Let me just quickly go there. So if you remember, this was our training data set in here. And let me find here. So remember, we had this data set that we loaded, and this data set comes from a library called DAG. So this is a library that we had before. And what we did is we split this data set in train and test. So this is what we did. And in the data window, we can see our training data set. And you can see here, there are 2,305 observations in the training data set. So what I did is I exported this data set into a file. And this is what I have. I have my data set in Excel here. And you can see that on each row, I have a record or an email. And across the columns, I have the features of those emails. And for those who missed the session last time, these features had a meaning. So let me start with the last one, yes, no. So this is the feature that we are predicting. So we are predicting whether, or classifying, you can say, whether an email is spam, yes. So that's value yes, or is not spam, and that's value no. And what I did in here, I did a count. So I counted how many emails I have. So there are 2,305, which is what we had in here. So this is our training data set that I exported. And out of that, 900 are spam and 1,405 are not spam. So remember that what we said is we create the Gini index for the whole data set initially. So in our PowerPoint, you would have the formula. So this is the formula here. So we are building the Gini index for the whole data set. So in this case, our classes are spam and not spam. So in Excel, you would count how many are yes. So how many are spam? And here you'll count how many are not spam. And then you apply the formula, which is 1 minus 900 over 2,305 to the power 2 minus the other possibility. So this is the formula here. Let me just make this one a bit bigger for you to see right here. So we are applying this formula in Excel. And we get a Gini index for the root, which is 0.4760. Now, this is our root node. And if you remember in R, we actually had that tree. Let me just, because I have a few other things in my R. Oops. Yeah, so this was our tree. Do you remember that from last time? And this is our root. So we have 900 that are yes, that are spam, and 1,405 that are not, which is what we have here. So now we have to decide how to split. Well, what condition or what feature should we use in this step to differentiate between our emails, to split the whole training set in two, basically. So the algorithm tells us that, well, we don't know initially how to do it. I just go back to our, slide. So we don't know. So what we have to do is for each variable, right? So
akamwaga food chini yote mbio hapo.
Sorry, I'm not sure how somebody can concentrate with that, but okay. So what we said there, that's what the algorithm does is for each input variable, it calculates all the possible splits and calculates this Gini impurity. Now, what we want is to reduce the impurity, right? So we want the impurity to be smaller. Right. So let's go back there in our Excel. And what I'm going to do is I'm going to follow this. And I'm going to say that the first feature or variable I'm going to look at is going to be this dollar. And if you remember, so this is the dollar, this is the column where I have my data. This was referring to how many dollar signs are present as a proportion of the text in an email. So the assumption being that maybe somebody's fishing for money or is promising lots of money. So the dollar signs appears, and that can indicate that the email is spam. Right. So this is what I'm going to do here. So if you look at this section in Excel, so this Excel, as I said, is in that folder I shared with you, is under decision tree. I've added it today, sorry. So I'm looking at this section. Let me put a border, right? So I'm looking at the feature dollar. Now, how many seats are there? Well, there are quite a lot, right? But of course, we rely on computers to find the right value. So what I did here is I calculated the maximum in that column. So if you look in here, I'm checking to see, okay, what's the maximum value that occurs in that column? So this gives me 3.26. So maybe 3%, the highest percentage of dollar signs as a proportion of the text from all my data set, my training data set is 3.26. And then I also want to take the minimum, but non-zero, because you see there's a lot of zeros here, right? So what I'm expecting that the split that I will do, so in this example is this criteria here, has to be a value between that minimum and the maximum, right? So in this example, you can see that they found it, the algorithm that we used, and it was CART, the same algorithm I'm explaining to you now. The value that was found was 0.056, right? So I did some of those calculations in here, right? So what happens when you take this value, right? The value will split the data set into two, so be the left-hand side and the right-hand side. And now I'm going to look in each of these sides, like the left-hand side and the right-hand side, and I'm counting again. How many spam do I have? So how many yes, how many no? So this is what I've done in here. So initially I'm saying, well, there will be how many to the left? To the left, I will have 1,740, which is the sum of these two. And to the right, I will have the sum of these two. So it will be 565. So basically this criteria will split my data set into two. of this size. And then in each of these sides, left and right, I will look to see how many are yes, spam, and how many are not spam. And you can see that, let me just make this one a bit smaller. I will basically obtain the same value that you see in this diagram here, into this tree here. And then I will calculate the Gini index, right? So the Gini index for this split is 0.3217. Now you're going to ask me, is this the best? Right? So, we need to make sure that this split is the best we can find. So one thing you can do to see this is to either use the solver. So Excel allows you to use the solver, i.e. the solver will be tweaking, putting in lots of values in here in order to minimize this value in here. Right? So let me change it, right? Let me change you. I'm not going to do the solver now. You can do that. But let me change this. And instead of 0.56, I'm going to put 3, the value 3, because you can see that this split can be anything between 0 and 3.26. So let me just make it 3. I think I have a little bit of a problem with my Excel on Mac. So I'm going to just manually calculate this, right? And you can see that the value of the Gini index for the split 3, so instead of having $ less than 0.056, I would use, for example, $ less than 3, right? The impurity, the Gini impurity index will go up. So it will be 0.47 instead of what I had before, which was 0.32. The other thing you're going to notice is that this is not a very good split because the two sides are very imbalanced, right? So I have a lot of stuff on the left and I only have 2 values to the right. So it's not balanced enough. And this comes back to some of the questions that were asked last time in terms of, how are these trees built? And we saw that we allowed the R package to find the tree for us. So the algorithm chose which attributes to use. Okay. So this is what's happening behind the algorithm. It will iteratively run all sorts of splits that can be done and choose the best. And it will build the tree in this fashion incrementally. So maybe let me ask if there are any questions up to what we've discussed now and feedback. Okay, so play around. Yes, go ahead.
I'm again from gene impurity. What is the meaning of gene impurity? I'm not understanding about that.
It's just that's how it's called. Basically, it's kind of saying how good is this split.
Okay.
Yeah, I don't know. Somebody came up with this name. It's not me.
Okay. Thank you. I understand that. Let us proceed.
Yeah.
Understand it.
Yes.
Let us proceed. Thank
Right.
You.
Yeah, you're welcome. Yeah, maybe it's a good idea to do a bit of research to see why is it called that way. But really, what you're looking for, I hope I've kind of showed you this illustration, that what you're looking for, you're looking to create a tree, a decision tree, that allows you to finally classify the data. So the final classification will be in the leaf nodes, which will be the last level of the tree, basically. And each split allows you to split your data set further. So you can come back with what you're looking for. Yeah. And this Excel gives you an idea of how these calculations are done. Now, if you want to run an optimizer, so you say, well, I want to find this value. So for my dollar, I want to find the value. You can use the solver. So Excel has a solver. So I've run this before I did this class, but you can say, my objective is K20, which is here. So that's my objective. I want to calculate the Gini split. And you do that by changing this variable, the split value. So you are trying to see what's the best split. And then you can add some criteria. So let me just delete this here. So your criteria can be that this value here is less than the maximum, right? So sorry, let me go back. That one is less than the maximum, right? So you don't want to exceed the possible values, yeah, which is the maximum and the minimum for the dollar column, right? And you can do the same for the minimum. So you want this to be greater than, and this would be your minimum here. All right. So the solver, what will do then? It will pick values between that 0 and that, not 0, but the minimum and the maximum, and will optimize to find that value. So you can run this, and then you will see the algorithm changing the values here and trying to minimize to give you the best value possible for that split. Now, of course, the algorithm does it in the background for you. Yeah, so you can see that it stopped, and it stopped to a value very close to 0.56. Okay. There's a question. Let me take the question. Yeah, so this is a bit new, but try to read the notes if you were not here yesterday, sorry, Friday. Okay, but let me move on. I just wanted, for those who wanted a bit more insight into how these calculations are done, you can simulate this with Excel. And I've put this Excel together for you so you can see how these are done. So let's go back to our PowerPoint. And let me do a slideshow. So in the PowerPoint, you have this explanation, and hopefully the Excel can help you. And then we run this, the building of the decision tree using R. So maybe a quick question: do people feel that we should go back and run this together or not? Again, because we did look at it last time.
Hello, my name is Omar.
Yeah.
I think we can run it together because I was not here last time, so that I might be able to see also what's going on. Thank you.
Okay, so let's go briefly through it. So what you're going to see, yeah, sorry, did you finish?
Yeah.
Okay, right, so what you need for this is to open in R. I'm going to close everything because it's just too much. I've got too much. So what I'm going to do, let me save this one because I was doing some things before the class. Let me close everything. So this is R. I'm in RStudio. And I want to close the project. Let me just save a few things. Okay, so initially you have nothing. And if you downloaded the two projects that I shared with you, you should be able to open the project using Open Project. So we have two, right? We have the decision tree and the height example. So in this case, I'm going to open the decision tree. It's useful to work with projects rather than open separate pieces of data, because you can also reuse some of the data you loaded from last time you had this project. So what do you have in this project? Well, you have files. So you have this file called spam.dt. So I'm going to open this spam.dt, spamdecisiontree.r, and this is the file that we will go through now. Now, there's a few libraries in there that you need, and I've added some comments why you needed these libraries. If you don't have them, you will have to install them. So you'll be using install.packages, and then within quotes, you add the name of the package. So if you don't have, for example, tidyverse, then you'll be installing tidyverse. I already have it, so I'm not going to install it now. So to know whether you have a package or not, you can run if you want. Run each line, and then it will tell you whether you have these packages or not. So that's it. I probably have some conflicts somewhere, but I'm going to ignore them all for now. So I've loaded all the packages that I need, and now I can read my data set. And I think last time I said to you that this data set is already available in the package for you, and is called SPAM7. So it has 4,601 observations, and there are 7 variables in total. And you'll be able to look at the data by loading the data in a variable. So let me load it into email data. So somewhere here, I should be able to see email data. 1 minute. Oops. I think it's sorted, right? Somehow. Email data, you see? So I have email data, and if I click on it, I should be able to see what's inside. So you can see there are 1, 2, 3, 4, 5, 6, 7 columns, 7 variables. And if I want to see what they mean, I can also type help spam7. And this will show me in the right-hand side window what is the content of that data set. What is the meaning of each column? All right, let me just hide this. Okay, so what are we trying to do? Well, what we are trying to do is to use some supervised learning algorithms to classify emails, right? So in the code, after reading the data, so this is our data, you can do some visualization of the data. I mean, it's quite basic what I've done in here, right? So you can maybe see how the data is split according to the target variable. So in this case, you can see there are more messages are non-spam than spam, which is what you would expect. So we sometimes call this class imbalance. Okay, so you can plot also to look at some characteristics of the data. So let me take out the spam email. So what this one does here is doing a filter. It's applying a filter on the data. So my data is called email data. That's the variable there. So what I'm doing here is I'm applying a filter on the data, and I'm taking out only those that are spam. So you can see the filter is on yes, no, and I'm only taking the ones that the ones that are spam, right? And then you can look at to see at some of the characteristics of the data. So here you can see that, you know, many spam emails do not have this feature, like they have 0 for this feature. And this feature, if you remember what it was counting the sequence of text with letters appearing in capital in the email. So, like text being written in capital. So it's counting the length of the sequence. Okay, and you can also look at other characteristics. And what I was saying to you last time is you can see that you can't just use only one feature. You have to use a combination, because none of these features is sufficiently able to help you detect whether an email is spam or not. Okay, so let's go now forward to run some modeling to see if we can create a model. So the first thing we did, and I was saying to you last time, is that we set a seed. And this seed is because we do a lot of random choosing, for example, from this data set. So we need to be able to replicate. So we always choose the same proportions, for example. So that's why we set this seed, so that every time we run the code, we can obtain the same results. They are replicable. What we do next is we split our data set. So you can see here, I'm splitting my email data into 2. And here I'm saying that there should be equal probability that one message or one email appears in the training versus the test. Okay, but you can change that. So what, if you look at this int array here in this window, let me look at it, if I have it here. Okay, let me run it. So, right. So if I look at my int data set, my screen is too small. Let me look for it. Int, there it is. One thing you see here, that what's happening for all those, it's an array, basically, it's an array of 4,601, which is how many emails you have. And to each email, it assigns a class to go to. So either it goes in the train or it goes in the test. And with those, you now construct your training and test data sets. So here you're saying in the train, put all the emails that have a 1 in the ind, in the index. Okay, so that would be train. And in test, put all the ones that have 2. So now I have my data sets, train and test. So you can see the train, there. 2,305 observations, pretty much half. Yeah, it's kind of split in half. Okay, now if you wanted to see what the effect of maybe something like this is, then you would rerun it. And let's run it again. And you can see that now I will have more observations in the train than I will have in the test. Because in the test now there are fewer observations. 897 versus, let me find them if I have them together somewhere so we can see. Here, train and test. So you can see there are more in training than in testing. But let's leave them to half, right? So I'm just going to rerun again. All right, and now we can use a classifier. And in this case, we are calling the rpart classification algorithm. And if you want to see what this does, you can open the library. So it's doing a recursive partitioning for classification and is using the CART algorithm that I showed you on the notes. So let's run this. I'm going to run the classifier. It's not giving me any error, and I'm going to plot it. And this is where you're going to see that tree that, oops, I should put this one, the tree that I was discussing initially, right? So now this tree was created by the algorithm, and the algorithm chose how to split. And you could see that I could actually replicate at least the first split using Excel. That's what I was showing you in here. I could narrow down to the first split, which is, let me just round. Okay, so you can see here that that was the best split that gave me the least impurity, or the least gene impurity for that particular split, right? And you can see there how many I have on each side, right, of the split. Okay, this probably is slightly different now, but probably because I'm running this. I have to look and see what's I mean, it's not perfect, right? Because it could be the rounding issue, a rounding effect, where there's a difference there. Okay, so let's go back. So I have my tree, my decision tree. And now the question that you are going to have, right, is how good is this tree? I mean, how good is this tree to help me classify the emails? The other question that you'll have is how many trees are there? How many trees can I build? And maybe another question that you're going to have is, what if I have a different sample, right? Because, you know, you can see here that, right, my sampling can change, right? So like here, I have more training variables. Yeah, so I have more in train than in test. Yeah, than I had before. So what happens if your sampling changes? Will this tree be different? And of course, the answer is yes, because the tree is sensitive to the sample you are using to build that tree. And this is one of the issues with decision trees. Okay, and so once you have the tree, let me just run this again. Yeah. You can see I've changed the sample now, and I have a different tree. The tree is bigger, right, than I had before, and it uses more features. In order to look at the accuracy of this tree, or how good this tree is, oops, am I still online? I hope I'm still online, right?
Yes, you are.
Yes, you
Okay, good, good. How is everyone so far? Are people following?
Yes, so far so good.
Yes.
Okay, great. If I want to see how good this tree is, I have to read a bit more about how we actually look at the accuracy, right? And if you remember those measures that I had before, accuracy in terms of true positives versus false positives, yeah, sensitivity and so on, there are measures that we also have to help us compare trees. And I've put a bit of printing what do you call these things? Printing formulae or whatever functions in here. So you have Principi. So this is now printing some information about the tree, and I've put some notes in your PowerPoint. So if you go to your PowerPoint here, I am explaining what these things mean here. So anyway, one thing you're going to see is that it tells you what the formula was to help you build that tree. Okay, so that's quite useful. It also tells you the variables used in the tree construction. And when we ran this yesterday, right, we used only three. The three were used. Of course, now that you look in here, still there are four, right? Let me have a look again. Sorry, 1, 2, 3 yesterday, and you see now I have actually 4 because I also have money as being included in that as a variable. The other thing you have is the root error. So the root node error is what? Is the proportion of, so 920 is how many are, I think spam, right? Spam, and how many are in total. So in total, you have 2,313 in this training data set, right? So I have a 39.775 root node error. Now this error has to be minimized, right? So I'll be looking at the errors that I get further down as I build the tree with respect to this root node error. And N is how many data points I have in the training data set. And then here I have these splits. And you can see that in each level, I'm increasing the number of splits that I have. So initially, 0 level, I have 0 splits. Then I do 1 split with the node, right? And then 3 splits, and so on. And the other thing you see in here is the error. So there are 2 types of errors that are being looked at. One is the relative error, and one is the cross-selection error. So here is the error where you are basically running this on many different types of splits or on the training data set. And you're trying to see whether if you vary the splits, how sensitive is the error basically of that tree. So I have some information in the slide about this. So that's called cross-validation. So you're running the same algorithm on different train test splits that you can think of. Different samples from your training data sets. That's more correct to say. And this also informs you how to prune the tree, because sometimes one thing that you're going to find out is that there's no point building the tree any longer because you're not improving the error. So you're not minimizing the error anymore. And you are not, it's basically computationally expensive. There's no point continuing. So this is also something that you can read through these numbers. And then these numbers can help you to decide how many levels you want in your tree. Okay, let's try to run a few things. So this is now showing you the relationship between this CP parameter and the relative error that you obtain. And of course, this parameter here that you have, so it's called the complexity parameter. So basically this says how much are you gaining, like how much more can you reduce your error without increasing the complexity, right, of your tree, because these trees can become very complex and very large depending on your data set. So at some point there is that trade-off between that threshold of complexity and how much you're gaining by adding extra splits in your tree. Okay. So this was, of course, for a different example, because what's happened here, I've actually ran this again and I obtained a different, a little bit of a different split. Okay, so this might not be correct. You'll have to do a bit of calculation to see what would be your best parameter to choose, complexity parameter. Okay, and we plot again, and you can see that I can cut the tree like this. I mean, this probably is not very good. It's not a very good cut. So let's try and see how good is this tree for predicting, because I've cut it, right? I've cut the main tree. And I can do that looking at the confusion matrix and the accuracy. And you can see the accuracy is not very good, right? So of course, I didn't split this in the right point. You will have to use my notes to find one, because this was based on a different example, right? So I give you an idea here that you're using, you're choosing to prune the tree where rel error plus X standard deviation is less than X error. So that's where you would, prune the tree. So maybe this could be your homework to see what would be the best split for the tree you had before. Let me just split the tree again. I mean, display the tree again. Okay, but I've already cut it. Okay, but let me just redo. Where would you choose now to cut the tree? At what CP value? Okay. Let me not choose that one, and I'm going to choose this one here. So 0, 1, 4, 1, 0, and see whether that improves. And you can see the accuracy has improved, because last time it was 0.7 something. Okay, so of course, what we've learned from this is that initially your algorithm can create a large tree. You have to decide whether the whole tree is enough in terms of the predictive power. And you will be using this complexity parameter to cut the tree to the level that gives you, a decent accuracy without being complex, computationally very complex. Okay, we can also look at the predictive now power of the model in terms of ROC and AUC, area under the curve. So for those who weren't in class on Friday, these are discussed. Let me just play it. These are discussed in the notes. So what I would like you to do is to go through them and try to read this so you can ask questions. Okay. So let me just run the code, and you can see. Well, I mean, there are lots of questions. Let me take the questions in a minute. Right, so you'll be able to look now and see how good your decision tree is, and you'll be able to plot this ROC curve. And as I said, this is a curve that plots the true positives versus the false positives, so specificity and sensitivity. And this line here that you see, this diagonal line, represents a random guess, right? I mean, we know that the random guess is like that because, it's 0. Yeah, it's half, basically. You can be right half of the time, but you want the model to be better at predicting than a random guess. So this is where you're looking at the measures of specificity and sensitivity versus each other. Okay, so let me stop here in terms of this example and see what questions are in the chat. Okay, there's some people who say, what we consider good accuracy. Okay, yeah. I mean, it depends, right? It depends a lot. And remember the discussion we had on Friday, how willing are you to accept a risk of having, false positives, right? Versus, versus, let's say, false negatives and so on. So there's a kind of discussion. You have to understand the implications and the risks of that. So there's a question, Florence.
All right, thank you so much, Madam. My question is about, I'm asking about fast accuracy. Like, I'm looking at here the result we are getting confidence interval. Like, how can we do it in Python? Like getting the confidence interval, those values like accuracy, area under the curve. Then another question is about the kappa, this kappa value. can it be used to compare two or more models?
Yes.
And then another question is about this p-value. Is it MC, that test value? That's something name I don't know. What does it imply, that p-value? Thank you.
Okay. So in terms of Python, I think I will let you research that, but Python should have a similar type of yeah, I mean, I can't get it from the top of my head now. I will have to look at the right libraries. So can I ask you to do that? I mean, this is something, no, my advice for people who program, is that first you have to understand what you're doing, and that's more important than the actual programming. And then you have to know which libraries are available to you and how to use them. But that comes with practice. So let me let you answer that question with Python so we don't keep everyone waiting for that. And in terms of this kappa, yes, it can be used in that way, just like you said. So this is basically calculating the rate of agreement that's better than a random agreement, right? And the meaning of this P is what's written on this slide. So you can see there are two P in there. So there's a P0, P, and the P0 is the rate of agreement. So how many times they agree? Yeah. Out of the whole, data set that they looked at. And then the PE, this is a hypothetical probability of a random match. Yeah. So if these people would be to rate something purely by chance, what would be that probability that they would agree? So this is how they are calculated as they are given on the slide. And that's the meaning. So you can use this kappa, you can imagine, to compare two models, because you can just say one model is like a rater and the other model is like another rater. Or you can use it for human annotators, for example, when they annotate something. So it's used for both, basically. Okay, let me see that and look at the time. So we can have a break, but 1 second. Right, so why do we need to train the data into split and test? Okay, and there's some answers there. So Martin, are you clear or?
Yeah, I'm fine.
Okay, so we are doing what's called supervised machine learning. If we were not doing supervised machine learning, we wouldn't have to split. Yeah, so the assumption is that you're using the training set to fine tune your model to come up with the best, line or feet or the best tree. And this model will then be used to, you will run it on unseen data, like real life data. So if you were to get an email, you should really be able to classify that new email that wasn't part of the test and the train. It's a new data point. Okay, let's see what other questions are there. Minimal size of the sample to split. Yeah, I think I agree with the answers that are given. I mean, it depends a lot, right? I mean, I've seen some work where, they would start with the 50-50, and the reason was that there wasn't a high confidence in the way the data was labeled. So sometimes you can also go back to the data that was labeled and correct mistakes of labeling. Okay, a large sample, okay. Good accuracy. Yeah, I think we discussed that. I mean, I did a research once that was looking at extracting specific information from legal text. And, production accuracy is close to 100%. So for somebody to deploy a machine learning, algorithm in, real life, like production, in some cases, the accuracy needs to be extremely good, like very, very good. Okay, so let's stop here now that we've done a revision on the decision trees, and let's come back and look at random forest when we come back. So let's split for how long, Joel?
5 minutes maybe.
Okay, let's do 5 minutes.
And in the chat, I'll just share maybe a simple trick question, more of like an icebreaker. So maybe you can tell us like if you were to choose one thing to have unlimited supply for it, yeah, for the rest of your life, what would that be? So tell us what you'll choose if you were to choose one thing to have unlimited supply for the rest of your life. You can just put it in the chat. Okay, great. It's good to hear most of you what you really care about. I think, Amelia, we can be back. It's 5 minutes now done. Over to you.
Okay, so is it time to regroup?
Yes, yes.
Okay, great.
Thank you.
Okay, so hopefully you had time to make yourself a cup of tea or water. So let me just share my screen again. Okay, so where are we? So we've looked at this example that was building a decision tree for classifying emails as spam and not spam. And then we talked about the fact that these trees can be many, they are sensitive to the sample that was used to build them from the training data set and so on. We also talked about complexity, that these trees can be very complex, and a lot of the times you can prune them, you can cut them. Okay, now I want to show you that there is another data set that you can use. So you can play around with this code, but if you want to look at a more complex data set, you can use this library, KernLab. And this library has another data set. Let me just go to the help. I've already run this. So this spam, there's a spam email data set that comes from KernLab, and is where our little data set comes from, right? Except that if you look at this other data set, you're going to see that it has many characteristics, like there are 57 variables, indicating the frequency of certain words and characters in an email. So it's quite a much bigger data set. There are more variables. So what you could do is you can try and see if you can find better variables to help you build a tree and improve the accuracy. So you can play around with the code and use this new data set from KernLab. Okay, so let me move on. So what I'm going to do is I'm going to close all. I'm going to close this project completely. I'm going to save what I had. And I'm going to move on to the next example. Let me just go back here. And this was predicting weights with supervised learning. So let's open that example. So you have it in the code I shared with you. So I'm going to open the project. And is in ML height example. I'm going to open it. And the same as before, you have some files. One of the files is the actual data. So the data comes as a CSV file, and it has these variables at the top, right? And I'm loading this into a data frame. And then you have the R files, the R file, which is, here, predict weight from height and sex.r. So this is the one with the code. And you have some images that I created. But, all right, so as before, we have some libraries, and we are still using the RPart library for building the trees. So this will not be a decision tree, right? This will be a regression tree. Why? Because I'm not classifying whether something is in one class or the other. I am predicting something. I am predicting the weight of a person based on their height and gender. So let me open the data. And the data looks like this. So you have the gender. So basically you have 3 variables, one of which is your target variable, but they appear in different units. So the height and the weight in inch and pounds, and then also in centimeter and kgs, right? And so you have the gender, height, and weight. And I think for those who were not there last time, this seems to be an interesting scenario, actually, and it's used in practice. It has applications in practice. So what we want to do, we want to import the data, try to look inside the data by plotting. We want to define the dependent. So this is the one that we are trying to predict, and the independent variables. So those are the ones that help us predict. And initially, we are not going to consider gender. So we are only going to doing weight from height. We will have to go through the same steps of supervised machine learning, splitting the data into train and test, and then creating some models. Back to R, and I'm going to just import these libraries in. There they are. Let me clear this. So I have them imported. I'm going to read the data. So of course the data, I've run this before. So when you save a project, it saves, it comes with the data that you loaded. So you don't have to go through all the steps every time you are bringing a new modification to your program. So that's quite useful. You can plot. Let me look. So you can see here I have 2 genders, and females tend to be less heavy, average, right? They are distributed. They have a different mean than the male, and also they tend to be not as tall, right? So okay, so the splitting, it's done very much similarly. So I'm taking 2 sequences, and then sequence 1 will be the training, sequence 2 will be test. A slightly different way of writing that formula than in the previous example, but the effect is the same. Okay, so let's run the training test. So now we have them. So we have training data and test data somewhere there. And we had how many observations? Well, in the whole data set, we had 10,000. You can see it here. So we have 10,000 observations. And then we split them in half, basically. You can see here that, you know, this type of formula as compared to the other one, it's not so flexible because it splits them in half, right? More or less the way it's written here. So you have 5,000 in more or less in test and 5,000 in train data. In training, yeah. Okay. You might want to extract the features one by one. So the weight refers to the 5th column. So the 5th column is the weight in kg. So we are looking at the weight in kg and the height in centimeters. So those are column 5 and column 4. So you can see that that's your weight, column 5, that's your height, column 4, and the sex is on column 1. So if you look in here, the gender is on column 1. All right, so let me run them again. The same for the test data. So you are taking the weight and the height as separate vectors. And the first thing we're going to do is create a linear model, so a linear regression model. So we are using LM. And then the way R writes this, I actually quite like R. I think I'm going to stick with R now and forget about Python. I don't know if anyone feels the same. I know somebody said on Friday that this is the first time they saw, you know, machine learning in R. So I don't know what they think about it, but it's quite nice. So when I fit this, I have this sign here, this kind of, I don't know what you call this, approximate kind of sign. And this basically separates the dependent from the independent variable. So on the left, you have the dependent variable, the one you're trying to predict. So in this case, we are predicting the weight. And then after that approximate sign, you put the variables that you want to use for prediction, right? So in this case, as I said before, we are first ignoring the gender. So I'm only going to predict the weight with respect to the height. I'm going to run this and plot. And let's put the line of fit in there. That's the line of fit. So one thing we see here is that, okay, this model now, it's not able to, differentiate between the genders. So it's trying to fit all the data. And if you want to see the coefficients, you can print fit. So you can see there that a fit was a formula. It was a line of fit using the formula that we've given, and you have the coefficients there. So you can actually build the line of regression using those coefficients. And then we can look at the errors that this line of fit has. 1 minute. Thank you very much. Tilde sign. Okay. Great. I think you've guessed English is not my first language. So I sometimes have complete mental block about what I'm supposed to say in English. Okay, let's continue. So let's now build the line. So the predicted weight is now this line of regression using the coefficients that were found for us. And let's calculate the error. Now here, I'm not looking at the type of errors you saw for classification. I'm looking at other types of errors. And the one that's used the most is the root mean square error. So that's the one you're familiar from statistics for sure. So I'm calculating the error and then let's print it. So one thing we see here is that the sigma is the root mean square error. And this tells us how far we are from the true value. So on average, we are basically about 5 kg, 5.54 kg out of the, outside of the real value. Okay. And then you have some measures that help you kind of look at the proportion of time you are correct, basically, or close to the real value. So you have there the R squared. Okay, but how about building a regression tree? So now we have a regression line, right? How about building a tree? So we do the same kind of process as we had for the spam email example, except that this is not called a decision tree now. It's called a regression tree because we are predicting a value, not classifying. Again, we set the seed. We split our data set into train and test. Okay. And then we build a tree. Now you see here that I'm forcing the model to use both variables. So I'm just saying, I want you to build a tree that predicts the weight in kg, but you need to use both the height in centimeter and the gender. All right. And let me plot the tree, and that's the tree it comes up with. Now, if you want to check this, okay, and another thing to say, this R plot does have more parameters. So even the type of the tree, I think somebody was asking last time, how do we put percentages in the node? We'll have to look at the actual help. Let's put a help here. Yeah, and we have the R part model and the plot. So you can see type 2 extra. So what are the arguments? So type, whether you want to split labels for the left and the right direction. Class model with a binary response. Okay, 0, no extra information. 1, display the number of observation. 2, class model. So let's put 1 to show us the number of observations, which we had before. Yeah, like 5010. Let's go back to help. You also have 3, the number of incorrect classifications. So you could, do that as well. And you'll have, but it's not that easy to see. I'm not sure what's happening, but right. Probability per class, let's put number 4. But I don't see the probability. Let's run it again. Okay, so you'll have to play around with this a little bit more to see what's the best tree that fits your how you like to view it. Okay, so at the moment here we have 5,010 observations. These are in the training set. This is it here, the training set, 500 observations. And the height in centimeter is the feature that's used to differentiate things initially, not the gender, right? So, if you want to see this in Excel, like I did, you can export this data in Excel and do some counting. And you can use that Gini index to calculate things to give you the right split, so you can see how it works. If we want to see some of the information on the performance, right? I see here there's some issue. Yeah. Okay, I'm not sure why that one is there, but we can see some information where to cut the tree so that the complexity of the tree is good enough. We don't want a bigger tree than necessary to help us predict. And you can take this in Excel and use that formula that I indicated on the slide. If you remember, we wanted that rel error plus X standard deviation was less than X error. And that point would be the one that you'll be choosing to cut the tree. And then you'll be able to prune and create a tree with the right complexity that you want. So let's generate some predictions on the test set. So we'll be using the tree on some new data. In this case, the new data is our test. And let's look at some metrics. And you see the metrics now. So we still have an error, but we are a bit closer to how we were with the linear regression model. So we are still over 5 kg in our estimation, but I think last time it was 5.5 kg rather than 5.2 kg. All right, so I'm not sure if there are any questions up to this point, so we can maybe try to move on. But that's what we try to cover on Friday. But I agree with you. I think it was too much material in one session, and it's worth spending a bit more time on this. But are there some questions? Training weight. All right, Florence. So I'm wondering if you run this in order. Let me see, training weight. You have to run all the cells, I mean, all the lines. Crispin, you have some observations. Would you be able to tell us?
Hi.
Hello.
Yes, okay. Please just display wherever you got your error. There,
Which one?
just here. Scroll down a
Yes.
little. Yes, here. Oh, sorry.
Yeah.
Yes, yeah, here. So, trying to look at the R squared, which is 0.853, and also adjusted R square, which is also 0.583. But I believe that adjusted R square is basically we are trying to penalize the model for extra variables, or rather extra, let me say extra variables that we are trying to include in the model. And since it's a kind of a penalization to ensure that the model is accurately fitted, so always I feel like adjusted R squared should be smaller than the R squared itself. But here I'm seeing both of them are of the same level. So could we say that the model is not well fit?
Okay.
Yes, because that
Yeah. Say
because
continue.
because adjusted R squared is just, it should be smaller than the R squared, because basically we know that adjusted R squared is trying to correct, or rather trying to penalize the model for additional variables that are being included in the model, and either they're not making sense to the model or they're making sense to the model, but now it's kind of coming to do with things like, let me say, overfitting of the model. That's why we call it a penalization, just to deter whoever is trying to do the trying to model to do the modeling of that, or rather to fit the model, not to include extra variables in the model, or rather decrease some variables in the model that might be important.
Yeah, you're probably right. Yeah. Yeah. So true, because the R squared
Just a second as our facilitator is coming back.
Hello? Hello?
Yes, thank you.
Hello.
You're back.
Hello,
Hello.
we are back.
Yeah, I'm so sorry. I don't know what happened. The internet just completely dropped. Yeah, so coming back to the question, I agree with what you say because the R square always increases when you add new predicting variables. I think maybe we need to look and see how these two have been calculated. And that could tell us why these two are equal. Yeah. I mean, in this model, for example, we have very few predicting variables, and we are using both of them. So after in the second model, I think in the first model, we only use one, right? Wait a minute, let me just look. Yeah, so in the first model, we really only use the height. Yeah, so there's another comment, let me see. Yeah, exactly. So there's no additional predictors there. I mean, one thing that you can do with this data set, which I'm recommending in the next parts of this R notebook, is to split your data set, because let's just plot again. See, like this model doesn't take into account the gender, right? And you know, you could say that you would need two models, right? You would probably need one for females, one for males, because they're just different, right? In terms of their profile. So later on in the notebook, I'm asking you to do that. I think, where is it? Gender here.
Sorry, we do not see your screen.
Oh, sorry, I forgot to share. Apologies. Thank you for telling me. 1 minute. Let me know when you see the screen.
Yes, it's up.
Okay, so one thing that I'm suggesting to do in class, we only go through part one. So part one would be the linear regression model, and part two would be the regression tree. And in this case, the regression tree is slightly better. But then, well, it's also using two variables, right? So you could maybe consider adding gender in the regression line as well. I am also giving you a little exercise here to add gender. So you can see that for the linear regression, you can add the gender either as being an additive or a multiplicative variable in your regression model. So you can either do plus here or multiplication. So let's try to run it since I suggested it. And, you know, we can see, let's have a look at our R square and adjusted R square. So even here, they are the same, slightly higher than what we had before. Can't remember what we had before. Let me just quickly have a look. 0.8853. So adding gender is better, is a better predictor, gives us a better predictor. And let's plot this. And you can see now the lines of feet for both the female and the male, right? I mean, you can't see it very well, but they're colored differently. So this is the red one for the female, and then you have this blue one for the male. And because it's additive, because I put a plus here, these lines will always be parallel to each other. But you can also play around with adding these two variables to have a multiplicative effect. Okay, so let's go back to this. There's something in the chat. 1 second. Thank you very much, Riri Bonje Johnson. Yeah, so they will always be equal when there's only one predictor because you don't have any more the other predictors to adjust for. Okay, thank you for that comment. Okay. So let's look at the same model, but now building did we build a regression tree? I think we did actually, yeah? I forgot now. Yeah, this is our regression tree that we built using both height and gender. Okay, now one thing you could do here is, and I'm suggesting that in the notes, you could maybe load a bigger data set. You can try and see how the tree will look like when you have slightly more data. Okay. So let's move on to random forests. Let me go back to our slides. So I think I should stop here with these two examples. You are free to run them and look through the notes. And as I said, if you have questions or comments, you can put them in the chat or you can email me. But I feel these two examples can give you quite a nice, introduction to these supervised models because it's easy to understand the data. I mean, I had a look at one of the data sets that was about mental health. And, some of those things are slightly harder to maybe grasp for the first time when you're also learning, supervised learning for the first time. So that's why I chose these two simple examples. Maybe just a comment to say here that, there is also what we call feature engineering. So in some cases, you don't rely only on, raw data that you collected, but maybe a feature that is a combination of some of the variables that you collected. So in this case, you might want to choose the BMI. So you can calculate the BMI, and then you can add that BMI as an extra feature into your model. Okay, so let's go back to our PowerPoint. And this is our example. You can run this in Python. I've added some notes for that, but I'm going to skip them now. And let's go to the topic of random forests. So we've done this. So we revisited decision trees construction using Excel. What are the issues with decision trees? So I think you've seen this already, hopefully, on the examples we gave. They are sensitive to changes in the underlying data. And I think you saw that I was running the spam email, right? And I had at some point a more complex tree than before. So if there's data, let's say your data changes, you are collecting more data. And most of these machine learning data sets, they're not going to be static, right? You will be collecting more data on your features. But these decision trees are sensitive to changes in underlying data, and they can change quite a lot. They take time to train. So the more data you have, I mean, we took a small example. So our data was small, and we could see these trees quite quickly. But if you have a lot of data, it takes time to build the tree. They can lead to overfitting. Why? Because you try to build only one tree. You try to build one tree that can capture the differences in your data, the differences in the features that you see in your data. So what can we do about this? So we have some options. So maybe just a quick kind of definition. So this term of bootstrapping refers to a random sample with replacement. And this concept of ensemble learning refers to the technique of building a set of prediction models. So you build several of them and then you average them in order to obtain the best. a single model with a low variance. So in ensemble learning, what's happening is the training data. So as we saw in our example, our training data is split into smaller subsets. And you learn a model for each of that subset. So that's how you'd be thinking about this, ensemble, that kind of, that suite of models that you've trained on smaller subsets of the data. But this is not always possible. Sometimes you don't have access to multiple training data sets. So you can use this technique of bootstrapping. So this means you take repeated samples from the same training data set that you have. And by that, you generate different versions. So different bootstrap training data sets from your data set. And then you train your model on these bootstrapped sets. And after you get all your models, you average the predictions to get the final model. So this method is called bagging. So in terms of our regression trees, maybe I should take some symbols out. You construct separate regression trees using these bootstrap training sets. And then after you construct all your trees, you average the resulting prediction. So I hope that makes sense. Up to now. So this technique has been shown to be effective and is an effective method in reducing the error. So for regression trees, what you could do is you can see how, so normally in a regression tree, what's happening is that the root error is decreased every time you split. With every single level, the root error is decreased. So you create these regression trees on the bootstrap data sets that you generated, and you average basically the root error over the trees. Average over all the trees. Okay, and that also tells you something about the predictive value of your trees. For classification, so this is an average, right? For classification, you add up. So you have all the trees, and then you add up the values, and that gives you the average predictor, if that makes sense. But hopefully we can take an example. So what is a random forest? So random forest is, okay, another problem maybe to say here is that because we use this bootstrapping from the same training data, right? There is a chance that the trees that we generate on these smaller training data sets will be correlated with each other. So the random forest aims at being a collection of uncorrelated trees. So the idea would be they are not highly correlated. And these trees are less complex. So you usually build only on a subset of the features. So they are less complex than building one decision tree. Hence, they have a lower chance of overfitting. How do we build them? So typically, you would have to use random features in each split to guarantee this uncorrelation. The other characteristic of these random forests is that they have these hyperparameters that you can adjust. And these hyperparameters refer to things like the number of data points in each leaf node. So I think we've seen those numbers in the trees we looked at, the number of levels that you want your trees to have. So that's basically the idea, that somehow we want to obtain this collection of uncorrelated trees. There are many trees, they are less complex, and we can adjust these hyperparameters in terms of how we build them. And now comes the question how to combine them, because we said that what we have to do is to combine these trees, which are all candidates, into one, basically one kind of predictor. So there are different methods. So the ensemble method, which we discussed before, so this combines all the results. This bagging also assumes that you build these trees in parallel, so you can build them independent of each other. The other method is called boosting. So boosting builds the tree sequentially. And the idea is that you learn from the previous iteration when you build your trees so that you can obtain a better score. Okay, so we talked about bagging. So boosting is similar in the sense that you can use it for both regression and classification. We don't create the trees independent of each other. So with bagging, we saw that what we do, we create multiple copies of the training data using bootstrapping. And then we feed separate decision trees to each copy of that data. So all those trees are built independent of each other and they can build in parallel. And then we combine these trees using an ensemble. So we can average or we can add up. Boosting is similar, but the trees are grown sequentially. And there's a relationship between the trees and there's some information being used. So it doesn't involve bootstrapping the data or sampling. Each tree is fit on a modified version of the original data set. Okay, so that's the theory. What are the advantages? So the advantages are that we eliminate correlation. So we overcome the correlation problem by forcing each split to consider only a subset of the predictors. And we usually use a small predictor subset from the total number of predictions. So this leads to both a smaller error over the technique of bagging. What's the algorithm? Well, the algorithm has the following steps. So you have a training data set that you want to use. You select the number of trees you want to build. So a number of trees, and then you start building the trees. So you have a loop, an iterative loop from I to the number of trees you select. You generate a bootstrap sample of the original data. You grow a regression tree on that bootstrap data. And then for each split, you select the variables that would be used for the split. So you'll be selecting a subset, M variables at random from all the possible P variables. And then we do, in a similar way as we build a decision tree, you pick the best split point among the M variables that you looked at, and then you create a node, you split the node. Okay, and you stop. When do you stop? Well, you have to have some kind of stopping criteria to determine when the tree is complete. And most of these trees are not cut, they are not pruned. So you build complete trees, but small trees. Okay, so hopefully this is clear, reasonably clear. So I have a suggestion that instead of me showing you something, that you look at this little tutorial, or we look at this together. It's quite a good tutorial on random forests. So let me give you a bit of time to open it. Let me just open it as well on my machine. Okay, it's about, according to this, 21-minute read. But yeah, might take us a bit longer. But what I'm suggesting is that you take a bit of time to look through it, and then not in 20 minutes, basically, to read this for tomorrow, because we meet tomorrow as well. And then you have hopefully some questions, and you have gone through this little tutorial, and we can discuss. The good thing about this tutorial that I liked, and that's why I chose it, is because it's using the same data set with the emails, with the spam emails. So you don't have to shift your thinking to a completely new data set. The only difference is that this data set is slightly larger. So this is the larger data set that I mentioned to you, which is the one that has, can't remember now, 50 something features. 58 variables. So the first one that we looked at only had four, and the one you're trying to predict. So of course, for something like this, with all these features, it makes sense to use a technique like the random forests, because you don't know which combinations of variables would give you the best predictor tree. So this algorithm will then select or create multiple trees, you know, how many you want, hundreds of trees, and then will put them into an ensemble and give you the best predictor. So what I'm suggesting is you go through this, and then we can discuss at our meeting tomorrow if there are any questions. Let me just quickly have a look at how many trees they build. 300 trees. So it's quite, I would say this is quite a good tutorial to go through. Okay. So let's continue, because I wanted also to talk to you about support vector machines. So hopefully you can now switch your mind from the random forests to this. So a short recap, we are still in supervised learning, and we start with a pair of input and outputs. So these are our data and the labels we are trying to put on the data. And we are trying to build some kind of model function that allows us to describe that relationship between our data and the labels. So the different machine learning methods, they only differ in the function that they build. So you saw that we had a line of regression. So one of them was a line of regression, and the other one was a tree. But they all really used the same kind of method of learning from data. It's just that the outcome is slightly different. So from a mathematical point of view, what we are doing is we are constructing some kind of optimization procedure. So for the line of regression, we are trying to optimize the line coefficients so that the line fits the data the best. And for the trees, we are trying to optimize the best kind of decision tree that we can build to fit our data. Usually in machine learning, you try logistic regression as being your first kind of option, but this may not perform well on data. especially if the data is multidimensional. And then you can go to something more complex, such as the support vector machines. Okay, this slide is revisiting some of the key points we discussed before. So the first one would be that the quality of the test data is important. And the other thing to say, it's not possible all the time to visually inspect the data. So for the data sets we looked at, we could, like, for example, the weight and the height example, it was easy for us to visualize it. And we could see the outliers and we can see how the data is distributed. But this is not always possible. And these outliers, which we sometimes can't visualize, can cause problems in fitting. So this takes us to maybe something that's slightly outside of the scope of this, and that is how we encode our data. So it's important to not only collect good data, but we also have to think how this data will be then represented or encoded for our machine learnings to play with and use. Another point here is linear models are fast, less prone to overfitting. And I'm wondering what I wanted to say here. Yeah, so when you have something like image processing, for example, an image can, in order for you to represent an image, you will have to rely on a multiple number of features, right? You have a lot of features. So, you know, if you want to represent everything that is in the image, then you have a lot of features. And most of the times that's not reasonable. So you will have to pre-process your data, but you'll be losing some classification power. Okay, now let me skip this. Yeah, I think this is another point, maybe just to say here that the linear model or the regression tasks, right? It's easier. I mean, you don't have to split, right, your data set, and you will still be able to get a good idea of the kind of error that you should expect. But in many cases, these output errors are not known. And this is when it's important to split into train and test. And, you know, that kind of partitioning that you are doing will be relevant. And in many cases, you do more than one type of partitioning on the data, and you'll be rerunning your models and checking how it performs. Right. There's a general rule. I think there was a discussion on the chat about what should be the split between the train and the test. And yeah, what I have in here, maybe that should be debatable, is that the training and the test size should be of equal size as being desirable. I mean, especially if you don't know the error that you are expecting, right, on the data. Okay, so that would be some key points. Now let's go in here and look at these images. So the first one on the left shows two classes of data. So you have the dark colored points and the gray points there. Actually, there are three probably, right? There are three types of points that you have. So if you were thinking about this being a classification problem, then your points will have to go into one of the three classes. And you can see that visually, you know, you see the classification, you see your points and so on. But sometimes you can have other situations where, might be a bit more difficult to see the separation of the data that you have, right? So, let me see here what I'm showing you so I don't give you the wrong reading. Okay. Let me come back to this slide in a minute. So let's go to the support vector machines. So the support vector machines is a supervised learning algorithms. And the good thing about it, it can classify both linear and nonlinear data. And it's based on the idea of support points and margins, and a nonlinear mapping to transform the original data into a higher dimension. So let me go to this example. And what you have here is two different classes or points that you're trying to classify. So the blue dots and the red squares. And you can see the way they have been displayed is they're already quite separated, right? But the question is, which line of separation is better? The red one or the green one? So that would be the question. Now, of course, the way we fit this line is fitted on the training data set. So we don't know what would be the real life point that we are going to see. So the choice of the line would be important. So the idea of the margin relies on this width that you see in here. So it's a rectangle that shows the distance between some points, and we call them the support points, and the line of separation that you see in here. So you can see that I have a rectangle in green that has a wider width. So that would be the distance between basically that line and the points that are on each side, the support points. So I have this blue and that red as being the support points, and then the other one. So the idea would be that I want the lowest margin. So the best decision line is one that produces the lowest margin. So I would prefer the red as being the optimal solution. So the idea of the support vector machines is to find that smallest margin. And here's a definition. The margin is the smallest distance between the decision line, which the one in green, and any of the training data. And of course, there's no point looking everywhere. You tend to look at the points that are closer to the line. So in this example, this circle point in yellow is closest as compared to the other red points to the line. So the optimization problem, so the support vector machine is an optimization problem and is trying to maximize the margin. So the margin is this distance, and we want the one with the maximum margin. And the data points that are touched by the margin, the ones that you see in there, are called the support vector or the support points. Okay. There's some questions here. Why is a bigger margin better? Okay, the largest margin. Why is the largest better? Okay, let me skip this one because I have a slide that makes that one a bit clearer. How to find the best decision line. So what algorithm could we employ to find this maximum margin? And the other question I had here, how does this relate to logistic regression? And we haven't done that. This comes from a different course. So let's keep that question. And let's have a look at this slide. So this slide now is talking about, gives you a picture of what are we looking for. So in the 2D case, you are looking for this line of regression. And this line is given by this equation here. So you have all the points that are above the line will satisfy this equation here. And the line is given by this equation here, a of x plus b of y. And all the other points less than, all these green points or blue are below the line. So we are looking for this decision boundary. And what we are trying to do is to find this A, these B's, and the C's that can help us find that best decision. Okay, just looking at the comments. So what we get as an input to this algorithm. So we get the same training pair. So we have the data and the label, or the input and the output. And they can come as features. So we can have an array of features. And usually we predict one variable, y. The other thing we want is weights. So we want the weights for each feature. So a bit like this, but instead of having just A and B, I will have multiple W's, or A1, A2, or A, B, C, D, and so on. So I'll have this set of weights that will give me the importance of each feature. And in combination, they will give me that line of prediction for Y. But now instead of regression, so instead of finding this A, B, and C through regression, they are found through a process of optimization. So we are maximizing the margin to reduce the number of weights that are non-zero to just a few that correspond to key features. So we are trying to narrow down, but similar to what those decision trees were doing. We are trying to look through all the features and only keep the ones that can give us that support vectors, and they best describe the data. So let's have a look at the algorithm. Let me just quickly have a look at the algorithm. I think I didn't put it in here. All right. Another thing to say to you is this idea of kernels, right? So let's imagine that we have these multiple features and we can't plot them. We can't visualize all of them. But what we could do is we could visualize maybe 2 by 2, or look at features as pairs and so on. And when we do that, we see that, you know, our features cannot be separated linearly. So we can't find a line of best fit for our features. So what we do then, this is another illustration here, that you won't be able to find, you know, a line to separate your points. You will have to be some kind of complex function, maybe like this circle here, that can help you separate the data. And how can you find such a function? So this is where the support vector machines use the idea of kernels. So these kernels are functions that lift the data that you have into another dimension. And you, in the other dimension, you can find where you can hopefully find a separation line. So if you can look in here on the 2D, it wasn't easy to find the separation line, but if you were to transform your data through some kind of formula to bring it into a 3-dimensional space, then you would be able to find a line of separation. So that's what this illustration shows. And once you do that, you basically go back into 2D and you convert the function that you found in the 3D into some function that is in 2D. So of course that means that, you know, your functions, these kernels, have to satisfy some specific properties for you to be able to do that, to shift between one dimension or one type of dimension into a higher dimension and back. Okay, people are still talking about the other issues, but anyway, let's move on. So we covered the theory. So these kernels, as I said, are functions that allows you to move your data from one dimension to the other in order to find a line of separation to best fit your data. And there are two types. There are linear kernels and Gaussian kernels. And as I said before, in order for you to be able to do this switch between one dimension, you know, a space with one number of dimension to a space with higher dimensions and back, these kernels have to be valid. They have to satisfy some properties. And these properties are mathematical. Okay, so you can either construct them if you know how to construct them, or you can use some mathematics, some known kernels, and then you can check that they satisfy those conditions, or yeah, you simply assume that such things exist for your data, and then you out, no proof. I'm going to skip this, but this slide gives you some types of kernels that are being used. So inner product is one type of kernel that is used to model the data. Then there's the polynomial kernels and so on. These are just an example, a visual example of the types of kernels you can use. So linear ones, so this would be for data that looks a bit like that in that image, or Gaussian would be the circular ones that you see in the image below. So hopefully this makes sense so far. So what's the use of these kernels? To map the input space, to change the dimensionality, to remove or detect irrelevant features. So what would happen that as you move to a different dimension, you might lose some features. They will become zero. So you can avoid this issue of overfitting by removing some of the features. Okay, I think I should finish with this as an intuition for approximation using kernels. So this is a bit like zooming into an image, right? So if you use Google Earth and you're zooming in and out, you don't actually how does the zooming gives you the impression of things being continuous? So you're really kind of getting closer and so on. So, you know, you don't actually have all the data. You have just representation of the data, but at given resolutions, right? So those resolutions are achieved by removing details from the image, a bit like the kernels. So when you zoom out, you know, you are going into a different dimension, and you will only see, you know, that kind of representation of the data. So the kernels would be something like that. It makes it easier to switch between more level and less level. So it's a bit like this Google Earth, looking at the data at different resolutions. So to summarize, I just want you to get the idea of what's happening here. And the idea is that we have data that is not easy to capture with linear models. So it's nonlinear. There are many dimensions. It's not obvious which features are relevant. So you can have hundreds of features. And what you're trying to do is to reduce your problem to something on which you can apply linear models. And for you to be able to do that, you need to use these kernel functions. And these kernel functions allows you to move your data from one dimension to another and back. So tomorrow, I want to show you an example of using support vector machines in R. But before doing that, I wanted to go through these concepts with you. So let me stop here to hear your thoughts. And we can continue tomorrow. Okay, I see one question. Maybe I can ask, I can wait a bit more for a few more questions. Yes, so there are libraries that allows you to find these kernel functions and apply them on the data. You know, so for the example that we had with the emails, right? If you take the email with the large data set, the data set with the large number of features, or 58 features, you know, you can see that, you know, you won't be able to build a linear model that can fit such data. And also, it's not feasible to think that you are going to build, you know, decision trees that can, or one decision tree, but then you have to, you also have the option of the random forest, right? And ensemble, that's fine. But supporter vector machines can also give you another option where you are trying to make sense of this multidimensional space of features, of 58 features. And of course, some of them might not be as relevant as other features. So you would, you know, reduce the dimensionality of your data, or you're looking at your data in a different dimension in order to help you find the most relevant features. In terms of class imbalance, yes, we can talk about that. Maybe if you have some specific thing in mind, you can bring it. I mean, of course, the support vector machines are used for classification. So you typically have two classes. You're trying to distinguish between two classes. So there are connections between, you know, how balanced your classes are with respect to how you are, what model you're using. And of course, the data can be dynamic, right? Because you are collecting data, you're constantly collecting data to, you know, it's not going to be static, right? You are learning from the data. So also the distribution between your classes might change. Of course, for the email example, you always expect that, hopefully, but it doesn't always follow. You expect that the number of legitimate emails would always be higher than the number of spam emails. Okay. I'm not sure I get that question, the last one. Okay, so the one class is 6.8 and the other is 93.2. I think the only relevance here, as far as my understanding, is that you know, you want your model to be better than a random guess, right? So if the classes are the way you give them, then of course there's a high chance of, you know, higher probability of something being in one, the larger class, right? Because it's larger. So you would want your model that discriminates well. So where you would need to look is how you split, how you create your training data set. So that's where you know, of course, your training data set has to be a representative of the real world. That is true. And, you know, your real world looks like that split. So this is where looking at the accuracy of your model is important, right? So you have to do some experiments, more experiments in terms of how you are training your classifier, because you want it to be a good discriminative, to have a better discriminative power than a random one would, right? Okay. I think these are very interesting questions. How different are these machine learning models from the ordinary regression models? Okay. Okay, doing a simple ordinary linear regression. Yes. I mean, what this boils down to is what you know, what information you know, which you can put into your model, right? So, and what you're trying to do is to make your error smaller. So you could just run a regression model, linear regression model on your data. Nobody stops you from doing that, right? Of course, in that example, you're only looking at 2 features, or maybe 3 or something like that. But it will become quite difficult when you have a large number of features. So then you'll be using other techniques to help you improve on your model. Okay, and the other thing maybe to say here, where could be a difference, is that you're talking about error that you know and error that you don't know, right? So let's say for the machine learning, you assume that you have this training data set, and this training data set is accurate, or it gives you an accurate guidance of how you would do things. It's basically information that you know. So sometimes with regression, you are discovering things, right? And depending on the sample you're looking at of the real world, that's going to affect the relationship that you see in the data. So in some ways, they are similar. It's just that you think about them a bit differently, I would say. But that's my answer on that. Bandwidth compute equal T. Another way to find kernels. I don't think I understand that, but maybe you're right, but I'm not sure in what context, what's T and bandwidth. Maybe if you can explain, that can help. Okay, maybe he's not online. Okay, so if you use PCA to reduce the dimension, do you still need to use the kernels? Mm-hmm. I think they're related, but a bit different in terms of how you're using them, these two. Yeah, so the PCA will allow you to, it's a linear method, right? It's a linear method that you apply to your data in order to reduce the dimensions, right? So kernels are not always linear, right? And it might not always be easy to find a linear method, right? For your data. Okay, I'm not sure what is this is in non-parametric regression analysis. Yeah, I'm not sure if I understand that. So I think these are techniques that you would, I mean, to answer the question, maybe there is, you know, you'll have to judge what is it that you need to use. So for the principal component analysis, you know, your data is assumed, or your factors are assumed to be highly correlated. So, you know, what you are trying to do there is you're trying to say, if all these factors are highly correlated, I don't need all of them, because they will be, you know, duplicated in effect on to my target variable. So you'll be looking to see how you could eliminate some of this redundancy, because your features are highly correlated. So I think it depends a lot on the type of the data that you have. Okay. Okay, fine. So there's some. So I think we can stop here. So we've covered the theory, more or less, of the support vector machines. And tomorrow we can see some practical demonstration of that. So what I can ask people to do is to hopefully catch up on the materials that were shared so far, send me feedback, and then tomorrow we meet and we start with a demonstration for the support vector machines in R. So that's all for me.
Okay, thank you very much. That was quite great. I think we captured a lot today. And we are looking forward to tomorrow. Thank you very much, and see you all, everyone. Goodbye.
Okay, bye.
Bye-bye.
Bye.
Bye, thank you. Bye.
Bye, thank you. Joel, please, will you share the materials?
Bye. Bye.
Bye. Joel, please share all materials.
Bye-bye.
Thank you.
All right, thank you.
Bye.
Please share them as soon as possible.